Dear audience, thank you for the opportunity. So I would like to present my PhD topic, which is in general the application of artificial intelligence in COVID-19 severity prediction. So I'm Márton Rakovics. Besides being a PhD student here, I'm also a statistician at Translational University. And my vision is to make AI an everyday tool in healthcare. So I'm trying to develop AI models to achieve this goal. I have two ongoing projects. The first is almost finished. It's a meta-analysis, and the second one is a registry analysis. This first meta-analysis is titled Investigating the Efficacy of Early Severity Prediction Models of COVID-19. You probably all know COVID-19 by now fairly thoroughly. So in general, there have been around 700 million cases worldwide so far, with around 7 million mortalities. And we saw, at least in the early stages, the characteristic of disease, this infection was this rapid deterioration of patient conditions. So it showed that it was important to identify possible severe outcomes as early as possible. And from a resource management perspective, we saw that, for example, in very developed countries like Switzerland, above 70% ICU occupancy, patient outcomes declined. So it was not only important to identify possible severe patients early, but to be precise with this and not burden the ICU with non-severe ones. Many severity prediction tools have been developed throughout the last couple of years, but which ones perform best is an open question. And it's also important for future development in similar cases. Maybe and new pandemics arise. So our aim was to quantify the performance differences coming from mainly the different tool types or statistical models. I will use these terms interchangeably. So we've looked at patients, COVID-19 positive patients who were hospitalized. We wanted to compare these different severity prediction tools, and of course we assessed their performance using the usual measures, area under curve, sensitivity, and specificity. Our hypothesis was obviously that deep learning AI tools would be better than other ones. We've identified close to about 27,000 studies, and out of those we extracted data from 430, so quite a substantial number. And of course, besides the sort of mathematical model of the severity prediction tool, there are many possible confounding factors that also have an effect on prediction performance. So we wanted to try to control for those. We used the MetaForest algorithm that was specifically designed to identify relevant confounders. And out of the many possibilities, we were able to identify sort of probably the most significant ones, and we did control for those. And we grouped the different tool types to three main categories: the more simpler ones, linear classifiers, the sort of machine learning models, and neural networks. They're also machine learning models, but we treated them separately because, as we'll see, they do. They do actually work better. So this is just the main finding, so to speak, in terms of AUC. So, you can see that the linear classifiers reached around 85% AUC, which means that if the model was presented with non-severe and severe patient, it could identify the severe one correctly 85% of the time. Both neural networks and other machine learning models are significantly better. There isn't a huge difference in AUC, but if we look at sensitivity and specificity, we see that it does matter a lot. So if we fix sensitivity at 20%, I mean false positive rates at 20%, there is a big difference in sensitivity. It's probably best to illustrate this with a hypothetical situation. Take 100 patients. Out of those, 10 are severe. Of course, we would like to identify those 10 patients without having many false positives. And if we compare two model types, instead of using linear classifiers, so classic scores, if we would switch to neural networks, we could half the number of false positive cases while also maintaining the number of true positives. So we could identify the severe patients just as good, but decrease ICU burden way more. So we could say that all in all, out-of-the-box machine learning models do work better than the classical ones, and specifically neural networks are the best. And so it would be important to try to move on from these very simple models as fast as we can in similar situations. I would say that our review was both unique, both in breadth and depth, and I think it can help guide clinicians in using the proper tools, and most importantly, help develop new tools for future situations like this. There are some limitations. Maybe COVID-19 severity prediction was an easy problem in a sense that even though we think of this disease as sort of a respiratory disease in some part, we saw that including chest scans with laboratory data did not improve model performance, interestingly. And there are possible other confounders we could not control for. And for example, hospitalization policies may be very different in different countries. And of course, we only looked at hospitalized patients, so that may be a sort of a selection bias. There, we tried submitting the manuscript. What got rejected, we're resubmitting to JAMA Network Open, hopefully real soon. And maybe some other. Okay, so building on the first project, the second project is the development of a novel deep learning severity prediction tool for COVID-19. Again, the data we're using is specifically COVID-19, but we are trying to figure out the general framework that can be applied to other diseases as well. Amongst other data sources, we're also using the COVID-19 registry and biobank and Corona app registry, which is our colleagues here at CTM are working on these registries right now, and I would like to thank them a lot and everyone who worked there, because of course it's essential for our project. I talked about briefly the background on the disease itself, but regarding the methods, a Nature Medicine review highlighted that there are two avenues of improving models in medicine. Transfer learning is one, so using external knowledge, external data relative to the specific problem, and also use of multimodal data, so specifically text besides numeric values. So we aim to do this, incorporate external knowledge into the model and build on textual data as well. We're still investigating COVID-19 positive patients, and we're testing out different prediction models and assessing their performance. The model type we found to be really good is called the graph attention network. It has sort of a similar structure to what you can find in ChatGPT. So this attention mechanism, and the way we're doing it is we're taking the registry data, so our numeric values, laboratory data, clinical measurements, and so on, and we're also taking data from external source, specifically a team at Stanford developed these medical concept embeddings from about 80 million medical texts. They were able to form vectors for 100,000 medical concepts, and we can construct a knowledge graph telling us how these concepts are related to each other, concepts here being what we measure for our patients. And using this knowledge graph, we could infuse this knowledge graph with our data, specific data, and we found that these together help increase the performance. On the right side, you can see that this graph attention transformer is better than one of the highest performing machine learning models, random forest. And on the left side, it's what's called the attention matrix. It tells us what to consider for the different measurements if we want to arrive at good predictions. So for example, if you look at MI, myocardial infarction, the green dots there in the row tell us what other measurements the model wants to focus on for encoding myocardial infarction to arrive at highly performant predictions for our COVID-19 problem. Thank you for your attention. This is the status. Right now, we've submitted the first manuscript, and of course, we're working on the other. And besides these two projects, I've been involved in several others during the last 2 years of the PhD studies. I've been a co-author of 2 D1 papers, 3 Q1 papers, and a bunch of others. I would like to end with this quote from Hegel: "The owl of Minerva first takes flight with the twilight closing in." I think, unfortunately, this is especially true for our COVID-19 topic. Thank you.
Yeah, it was fantastic. We did some studies on A-drop and CT, and there are others. What I was missing is imaging. Can you put in imaging results like CT? Because we know that the chest CT pattern and also the percentage of infiltration of the CT was one of the major confounders of outcome in COVID. And the second one, which I missed, is LDH. And LDH, again, because of the hematology and also because of the chest, I think should be included. Maybe it was just not picked up by these trials. For instance, on this one, I can't see either CT or an LDH, but that might, of course, it's always easier to put what is not on the list. Of course, there is a lot of things you already did, so congrats for that.
Thank you for your comment. You're absolutely right. So imaging is important. What we found in the meta-analysis was if you have sufficient number of laboratory and clinical measurements, surprisingly, doesn't give you that much. So it's sort of interchangeable. But I'm not truly trusting that part of our results. So of course, for this graph attention transformer, it's possible to use imaging, but it takes so we would need to modify the model pretty.
And it's difficult to quantify, so there is no standard score for that, right?
Yeah, we would probably. I mean, the approach usually is to do things what is called end-to-end, yes. Meaning that you just feed in the data, even if it's different. So one is just numeric, the other is imaging, and even text, and just pick up at the end the sort of the prediction. And of course, it's not the best because it works like a black box sort of. This is one way to try to open up this black box by, for example, looking at this matrix of associations. But it's a tough thing. So yeah, and sorry, just LDH is not here because it just wasn't measured for that specific study. So for which the knowledge graph was constructed. But in other cases we have that, and of course we use that.
Wonderful work, especially looking ways of presentation that looks like the molecular studies. We spoke about imaging and prediction. You said all good works come much later on. It's true, COVID is a way, but could be example of the future of rare disease. As a dermatologist, you could expect what I'm going to say. We had developed almost a map of dermatological manifestations, most of them coming from Spain, where you can define exactly, repetitively, specific clinical signs that define prognosis. And I would like to ask you if you had the possibility in your studies to include these dermatological pictures. This, of course, will make us very lucky because I had done a little bit in this period, this work, not systemically like the Spaniards, and I have the feeling that dermatological signs could somehow define prognosis. Did you have the possibility, and do you have such data?
I didn't search for image data specifically. In the meta-analysis project, of course, that wasn't just a focus. And for this second project, again, I wanted to look at databases that are built similarly to the study databases from the meta-analysis to be able to make comparisons. So I wanted to sort of try to show that our model for the data sets we could find, works as good or even better than the ones we found in the different studies in the meta-analysis. But what you're saying is really interesting. So we could probably focus more on imaging. But I'm not sure how easy it is to get hold of these data sets.
For us, it would be even enough if we say with or without dermatological signs, whereas we have now very clear specific dermatological signs associated with the COVID-19 infections. And for the future, I can tell you if we speak about viral infections, generally in dermatology, we can diagnose in many cases which virus it is before we make any laboratory test just by the clinical picture. We have so specific clinical picture for viral disease in dermatology that if you put it in your work now, it will help us in the future to include them in further evaluations. Yeah. Because I fully believe what you said, neural networks will be the future, because up to now we make classifications by the belly. In the future, we will make classifications by objective means. And I think dermatological science will be included more and more in this, according to what we know. But up to now, we were a little bit ignored as dermatologists in being included in such kind of evaluations.
I would also have a question regarding imaging. You mentioned in your presentation, also in your answer, that including imaging wasn't making the results better or the evaluation better, basically. And these studies, which included imaging, did they always use the actual images, like the chest X-rays, or the CTs, or only the scoring systems, and like also numerical data, basically, because that could also introduce some bias or...
Yes, that's a very good point. It was very mixed. So in some cases, the raw images were used, and in other cases, radiologists assigned some different scores, and even those scoring schemes weren't the same for all the studies. So when I said this comparison, we weren't able to sort of differentiate between these different measurements of the images, but in general, doesn't matter how you sort of process the image. In any case, it seems as though it doesn't make much of a difference.
Was your first project rejected straightforward from the editor's desk, or had it undergone review?
No.
That was a straightforward rejection.
Yeah.
What a pity. Yeah. Anyway, good luck with
It's not anymore like it was.
This is leading to my next question, your comment. That because I think that the real value of your two studies is not COVID-19, it's AI and this neural networking. So what would be your explanation or your argument that your work is feasible for any further diagnostic challenges that we face in the future, regardless whether it is a pandemic or a phenotype of a disease or whatever? Rare disease or what? So what would be your argument as an expert in that field?
Yes. First of all, I would say that even if we don't use neural networks, simply using machine learning models, which are really easy to implement, just a couple of lines of code, also showed to be much better than the logistic regression and like simple scoring schemes most often used. We would first of all suggest to just go right off the bat with these machine learning models. You don't need more patients than for the other types. So we've looked at the performance as a function of number of patients included, and actually you don't need more patients for machine learning models than simpler ones. That's one thing. The other thing is for more sophisticated neural networks like that one we are trying to build, this simply building on a huge amount of external knowledge, that's also something that I think is applicable everywhere and should not be ignored. If we know, because that's just a lot of knowledge you simply disregard if you only work with your specific small data set, whatever the new disease may be. So that doesn't seem too rational if you can include previous knowledge, because if it doesn't help, the model won't use it. But if it does, then it will, of course, help your prediction.
This will make single center small studies obsolete in the future.
I just have one question, and maybe it's just you can clarify if I understand it wrong. In oncology, we have usually many parameters that we are using to predict outcomes, and usually this is a very hard outcome. Patient dies or stays alive. And what you are suggesting, if I understand it right, is that basically if we would be using, instead of these parameters alone or maybe in combination and using it as a linear model, we would be using and putting them into a neural network, they would be much better predicting outcomes.
There's this potential, yeah. If your current prediction techniques are not good, so if you found very specific markers that are excellent for some disease, then probably not. But if currently you're not very good with your predictions, then
we are not really good.
I'm pretty sure that there's a chance to improve that, yeah.
I mean, we come now to a totally new concept of future medicine. I see the danger here. I mean, you are an exceptional case that you look medicine and technology together in one person. But looking at this, especially for rare diseases, the danger is that looking on the old classifications we have, the terminology is totally different. So it ends to a chaos. So first you have to work paper per paper, word clinical style to clinical style to make a common wording, which is incredible work, before you add on all this data, trying to make networks and comparing new classifications to the classical classifications, clinical classifications of phenotype. So who is going to make all this work? I mean, you have used one COVID, but if we say artificial intelligence is able to get more prediction, first we have to say, when we say nausea, it has to be nausea. Nausea is different than vomiting, and it's different than fever, and so, or increased temperature. So we have to have for each thing always the same terminology. This is almost impossible.
Yeah, unfortunately, fortunately, that's not the case. So these large language models, like the ones underlying, for example, ChatGPT, are very, very good at this thing. So you can word it completely differently. It still is able to extract that. This basic is probably the same concept. So just going back to this medical concept embedding thing, that's exactly what it's good for. So even if you have different terms for the same thing, the different words have these vectors assigned to them, and these like 500-dimensional vectors, these numbers don't mean anything in themselves, but you can compare these numbers for these vectors for the different words, and you see that if these vectors are close, that even though they're completely different words, then they're basically describing the same thing. So that's the strength of this.
I ask this because we just work on the definition of acne with different artificial intelligence models already existing, and getting the data that we have asked experts to analyze and then evaluate, I see that there are huge differences from one system to the other. So maybe you say it's doable, but what is now existing is very, very, very variable between the different systems. And no system is perfect. As we say, this system is so good and the other has worse. We see in every question we put, each system performs differently, and there is an optimum for one disease like acne, which is a common disease. So it seems that it's a lot of work to be done still, but I fully agree with you that this is the future, the way to go, especially for difficult questions where biomarkers are not existing.
Comment for that. So the big problem is that we have no registered data. So when you say expert, it means that the expert could look something, and I know because of the small things, and that small things that is making the expert regarding the conclusion is not written down. That's the big problem. If we have a good registration of data, the work with the AIs is very straightforward. That's what we have to learn to write everything down. Need the data. Yes, I'm trying to tell it, for example, in some conferences, the doctors write down everything. We have no time. Always the comments, no time.
Have you heard of the term technical physician?
No, technical
Have
physician.
you? Yeah, I mean, it is a valid entity now. I know exactly, because I was approached to take part in that in Holland, in the Netherlands, and technical physicians. There is training in a technical university, and they call them technical physicians. And I was asked to be the chair of the applied cardiorespiratory physiology. So, I mean, you are really a new era of medicine, and I'm sure that we are approaching that era when we will collaborate more intensively together.
I would like just one comment on this. So, while doing the meta-analysis, reading through all these studies, it was really easy to see the background of the authors. So, the healthcare professionals, reading their articles was way better than reading those who are based just from machine learning background, who have no knowledge of medicine whatsoever. They use different performance metrics, different way of describing it. It was very bad. So if it would be possible, I would try to push sort of healthcare professionals to learn more about statistics instead of the other way around.
The founder of this technical physician school in the University of Twente, which is within the first 200 universities in the world, she said that she is a clinical psychologist, and she said that physicians are very good at the bedside, but bad at thinking, pragmatic thinking. The engineers are very good in pragmatic thinking, but obviously no knowledge at the bedside, and she decided to combine that. So we all agree, and I think this is the... I was thinking that this is the famous last word, but if you want to make the famous last word...
I leave it the last word to you.
But before the next to last famous...
No, it's okay, but I was very happy to hear what you said, because this is what I believe. We have to go as physicians to the new technology, not leave them at the engineers. It's difficult, but we have to do it. Next generation, young people.
Absolutely. Well, thank you very much.
Thank you.